Okay, so this is the chapter or the section of the week on determinants. I'm going to try to make this more motivated than just a bunch of formulas, but okay. Okay, it's coming up. Okay, so if we can think of, so here's the idea. Every vector space is isomorphic to one of the R to the n's, right? We know that because any vector space of dimension n is isomorphic to R to the n. And one of them we have is the vector space is the arrows in Euclidean space. Euclidean space is just the space that has the geometry with lengths and angles, like we just a couple in the previous chapters that we messed with to deal with orthogonality. So let's consider the special case for inspiration of R2C. Well, and the idea here is, how do we have let's say we write two vectors like this, say V and W, right? Well, how do we know whether they're linearly independent or not? Well, in other words, if we have a coordinate system and these have coordinates, it's obscure. It's not obvious just from looking at the numbers. But if you look at the geometry here, you can see, well, if you have two vectors, and if you're in R2C, or if you have two vectors, if I look at two vectors in any of these spaces, they're always going to be in some plane that's inside one of these bigger spaces. So this is pretty sort of a general case for asking that two vectors are linearly independent. And so here's the idea that it's clear that for two vectors, the way they're linearly dependent is if one is a multiple of the other, right? Because the only way, if they're linearly dependent, then W equals some number A times V, where A is not equal to 0, right? So that means that there's some linear combination of V and W that equals 0, which is the idea of linearly independent. So if we look at it geometrically, we can see that, well, let's say we can make these two lines define some kind of area in here. We can define it in many ways, like we could just make the triangle, right? And there'd be an area A in here, and you can see that if A equals 0, these two vectors are linearly dependent. And that doesn't depend on how they're oriented, right? I can think of them in this way. And if area is not equal to 0, they're linearly independent. So the area seems to be a geometrical quantity that detects linear dependence and independence. And you can see how this would go to higher dimensions. Like if I had three vectors, say if I was in R3C, then, well, each one of these vectors couldn't be in the plane between two of them, but you wouldn't want one of the vectors to be in the plane of the third, and that tends the same way. You have some volume in here that does the same thing, that if V, the volume was 0, you have linearly dependent, but if V is not 0, you have linearly independent. Okay, now the question is, so the inspiration for determinants is, and if you go to higher spaces, you have hypervolumes with the same story. Okay? So the idea, though, is that we want to choose a particular kind of area that respects linearity. In some sense, if I ask, what are the row operations doing to these areas? I want it to not change, to sort of act nicely with respect to those row operations. Turns out a triangle doesn't, but there is one kind of area that does, and that's a parallelogram, right? Too many L's. Okay, so let's look at a special case as a rectangle. So let's look first. Say here's some coordinate axes that define some directions. And then let's look at just a simple case of, say, this vector here. Well, let's say that it is a 1, 2. So this vector here is going to be a 2, 0, because our translation is the x and y coordinates of a vector are the x coordinate up top, the y coordinate down below. You're used to in most math courses dealing with coordinate pairs like this, but we're dealing with column vectors here. And let's deal with the other one. Let's say, let's have it a little bit different. Let's say it just goes up 1. So this one is 1, 0. So the parallelogram here would just be the rectangle, right? And so this has some area.
Oh, maybe 0, 1.
Yes, you're right. This would be, sorry about that, would be 0, 1, right? Okay, now this has some area, and let's ask, well, and then if in general, we could have, this could be 2 and 0, but let's ask what happens if I then thought of these two vectors as it sort of like let's think of them as doing row operations between them. Here's 2, 0, and here's 0, 1, right? This is the first vector and the second vector. And I could ask, well, what happens geometrically? If we look at the various row operations we could do. So we can think of this almost as like a 2 by 2 matrix. And we can think, well, this just collects these coordinates. And we ask, well, what about the row operations? Well, I could, let's say that I just multiplied. If we have some area here, we can normalize this area. Let's just say it's an area here, the area of the parallelogram. If I multiply this first row, say by some number, what it's going to do is, let me extend the coordinate axis out this way. What it's going to do is it's going to multiply, say, this 2, say if I multiply it by 3, I would have 1, 2, 3, 4, 1, 2, 3, 4. I'd multiply it, so I'd have this vector here, and I ask where the new area here would actually be, you know, since I'm multiplying this one side by 3, under the row operation row 1 would be, say, 3 row 1, the area would go to 3 times the area, right? 1, 2, 3, because I'm making one side 3 times as long. And you can see that if I then made 2 times row 2, that would make it 2 times up here. That would sort of double the whole thing up here. So the area would go to 2 times the area. So that if I multiply, and this is going to turn out that, of course, that's sort of a simple one. We want to look now, what happens, let me redraw this picture now of just this here and this here, and say, what happens when I do like, if this is V1 and V2, and if I do, say, a 2 row 1 plus row 2, what this does is this adds 2 times row 1 to row 2. Well, if I add 2 times row 1, well, that's 1, 2, 4, 1, 2, 3, 4. It's adding this vector here, right? That's 2 times row 1. I'm adding it to this. So the sum is then this one here. Now, if I add it, then if I say, well, I'm going to look at the parallelogram. So that is going over 1, 2, 3, 4, 5, 6, 7, 8 over here, like this. Okay, well, to look at the area, let me draw, this is a little bit, let me just draw a parallelogram and ask, because you can see that the original length here is the original here, and the height is here. So if this was L and this was H, the area would equal the base here times the height for the rectangle, L times H. But now, after I do this, I have a parallelogram, right? We draw it down here. And I can say, well, this is L still. And this is H. What's the area of this parallelogram now? This is the new, this is the area of the rectangle. What's the area of parallelogram? Well, you probably can sort of, one of the ways to do this is to embed this parallelogram in a rectangle. And then I can see that this length here was, I've moved this over so that this length here, A, is the same as this length here, A. Okay, so the point is that this little triangle here is, the area of this triangle is 1/2 A times H, but over here, this area here is 1/2 A times H. So the big area now is, of the big rectangle, is L plus A times H, okay? So that's the area of the enclosing rectangle. It's important that you sort of see the geometry, because otherwise so here's the big rectangle, and this is the area that I want in here, okay? And I want, so that I've got a triangle here and a triangle here. Each of these triangles areas is 1/2 A times H. So this is the area of the big rectangle. Okay, well, if I make that so that that's LH plus AH. Well, if I subtract, the area that I want will be this big area minus this area and this area. So I have to subtract off A is going to equal L plus A times H equals L, minus 1/2 AH minus 1/2 AH. And you can see that this is AH, this is minus 1/2, minus 1/2. This is just going to equal LH, which is the original area, L times H. The point is that the area of the parallelogram is, even though it's shifted over, is just, I don't know if you remember, this is just the base times the height. This is the derivation of this. This is saying, okay, for a parallelogram, then draw the enclosing box here, and you can see that the area you want is the big area, the rectangle, minus these two triangles. And since the big area is made the way it is, it cancels, and you have that the area doesn't change. So a parallelogram is nice, because what we were doing was we were looking and saying, okay, well, if we have a row operation on this, it just shifts the rectangle into a parallelogram. Now, the same thing happens if I have, let's say I have two vectors in they're sort of oriented strangely, right? Here's one vector, here's the other vector. Now, what I do to add one vector to the other is say, okay, well, this vector, I want to draw sort of a little, if I can, This goes over 1, 2, 3, and up 1, 2, 3, 4, 5, 6, 7, 8. So it goes 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So there. So that will get me more clearly this thing. So if let's say this is V1 and this is V2. Well, this has some area, which is this length times this height here, right? This is going to be the L. So we know that this is just L times H, right? Because it's the base times the height. Now, if I add, let's say, 2 times it's like 2 times row 1, which is V1, plus row 2, which is V2. That's going to be adding this and another copy of that. So I'm going over this way, and this will be my new vector, the new row 2, but this will be the old one. So I'm going to end up then with another parallelogram, but you can see that it has the same base and the same height, because what I'm adding to the second vector is a multiple of the first. What I'm trying to motivate is the idea that a row operation just takes a parallelogram and sort of shifts it over without changing the height. So the area here and here are the same. Okay, so whether or not this is convincing or not is true. And the point is that, so we can see that a parallelogram has a nice, if I change the coordinates of the edges of the two vectors, right? What is going to be? I've got to, okay. If I treat the ends of the vectors here, like if I have, say, okay, go back and actually think hopefully with this. So let's say that I have one vector here that in the coordinate system is x1, y1, and another one here that's x2, y2. And what I can do is I can treat, if I consider the matrix x1, y1, x2, y2, to sort of think of them together here like this. And then if I make if I sort of transpose the matrix so I'm looking at x1, y1, x2, y2. This is what we did above. Or you can start from this just thinking of these as row vectors. Then it turns out that these vectors define an area, right? And we know if I do a row operation, like A times row 1 plus row 2, or vice versa with row 2 plus row 1, the area doesn't change. I also saw that if I multiply one row by a number, if I do R row 1, then the area goes to R times the area, the new area. So the point is, now it turns out that if I put these two together, then if I interchange the two vectors, if I do this row swap, that sort of interchanges these two, which interchanges the two vectors. It turns out that A goes to minus A. You can prove that these two things imply this. If you choose your numbers carefully, you can show that this has to occur. Well, it turns out then that the area of if I take two vectors, the area of a parallelogram defined by two vectors plays nicely with row vectors, with row operations. So it turns out then that this is what you know is a determinant. The determinant is basically the area. It's like if you take a set of vectors in some space, they form a parallel pipette or whatever it is, some or hypervolume And if that volume, if you define that to be the parallelogram that's defined by those vectors, then the area, then whether it's zero or not, that area that area is the determinant of this matrix. And it's going to turn out that the reason is because it behaves nicely with these row operations. So I'm trying to motivate that there's a connection between determinants in these areas. The text doesn't take this point of view, it sort of treats it at the end, but I'm trying to show you that it turns out that parallelograms have nice properties with respect to row operations. And this is true even in higher dimensions. If I take in 3 space, I take 3 vectors with 3 components, the same thing is true. So what we're going to do is, we're going to say for each n, we're going to look for a map. We're going to call it if we have a matrix M, which we can think of as here like x1, y1, x2, y2, and we can think of the determinant of M, we want it to have these properties. So what we're going to say is that this determinant is a function that it behaves nicely. So that what happens is that if I do a row operation, a row I plus row j, then the determinant, there'll be different matrices because I've done the row operation, but the determinants will not change. So what happens is this, that we write this notation differently. I do on M, let's say A times row I plus row j, and that goes to M prime, some matrix, so you apply the row operation. Well, it turns out the determinant of M, we want the determinant of M to equal the determinant of M prime. We're going to say this is if the determinant's this area, then this has to be, this is our property 1. This determinant doesn't change under row combination operations. And that if I do a scaling operation, if I do R row I on say M, that produces an M prime, well, we know that this determinant here is going to equal R times the determinant of M, because this was the original small area. And if I multiply a row by one number, it's going to scale that up and make it R times as large. So here the two are equal. Here, the transformed one is R times bigger. Well, that's our second operation. And then the third one comes if I do row I, row j, then it's going to turn out that the determinant of M prime equals minus the determinant of M. And that follows from the first two. So our attitude to determinants is we're looking for a formula for each n that has these properties. Okay, so where these properties are that the determinant, if I do a row combination operation, the matrix doesn't change; it's equal. If I do a scaling, it becomes larger by a factor of the scale that I multiplied by. And if it, you notice that these two rules are really this sort of like, if I choose minus, this is not quite the same, but it's similar in the sense that if I swap two rows, that you get a minus sign here. Okay, so since there's a parallel here, the notation is we can write determinant of M equals and put the row operation above the equal sign for the determinant instead of this two-step notation. So, okay, now let's first of all just let's see what this means. Like if I take a matrix here, like 1, 2, 3, 4, and well, here's the thing, the determinant of this matrix, we could say that the determinant of 1, 2, 3, 4, this notation, right? But what we're going to do is we're going to use a simpler one, like vertical straight bars with no little hooks. And we're going to say this is equal to this is our notation we'll use. Instead of having to write writing in Lex, you'd write /det would come out as text, even in math mode. So instead of writing this, we're going to write this. This is a number. This is going to be a number. It's going to essentially be the area given by, if I use these as vectors, this is going to be something like the area. It'll be plus or minus the area of the parallelogram defined by these two vectors. Okay, but let's see what that area is. And then we can actually draw the picture and see if it's the same. Well, what I can do is I can say, let's do, what would the row operations be to put this into echelon form? Well, we would do let's say minus 3 row 1 plus row 2, right? Well, if that's not going to change, the determinant should be the same. So we do this, and then we take, that'll be minus 3 times this is 0, minus 3 times minus 2 is minus 6, 2 3s is 6, plus 4 is minus 2, right? And then, because they're the same, now this is an echelon form, but we could also do the following. We could say row 2 plus row 1. That's not going to change the determinant, and that's going to lead to 1, 0, minus 2, 0, right? Okay, now we can take this and multiply it by, now let's say that if we take this and we want to multiply it by 1/2 row minus 1/2 row 2. Okay, now what does that mean? That means that this matrix here is going to be, we want to have that, I'm going to write it down here, equals 1, 0, 0, 1, right? Because I've multiplied this by minus 1/2, but that equals minus 1/2 times 1, 0, 0, minus 2, because this is the original one, and so this is the original area, and I actually did this row operation, which reversed the direction of a vector and changed it by shortened it by 1/2. But that changes, that's what I want. Now, if I look and see, what I'd like to do is be able to say this is equal to this. So if I can see if this is true, then 1, 0, 0, minus 2 equals minus 1/2 row 2 minus 2, 1, 0, 1, 0. Sorry. 0, 1. So it looks like to go from here to here, I just factor out the minus 2. That's much easier than thinking of it like this. So if I'm going to skip down here and say that what we want to write here is this. This is just an explanation. We'd like to write as equals minus 1/2 row 2 times minus 2, 1, 0, 0, 1. Well, what is this vector? Well, that is the vector that goes over 1. That's 1, 0 here, right? And this one is 0, 1 over here. Well, this length here is the length 1, and it's natural then to take this area as 1. So we're also going to, this is the identity. So we're also going to define the determinant of the identity equals 1. Okay, this is like a normalization. So this is equal to minus 2. So the claim is, that means we've started from a matrix and used these operations and come to a minus 2. Now it turns out that it turns out that this, you might add, there's only one function, sort of area, that works nicely with these row operations. There's no other sort of magical volume that somehow has these properties with row operations. It's always the parallelepiped of parallelogram, the hyperparallelepiped, or whatever you want to call it. So as a result, the determinant associated with it that has these properties of acting nicely into the row operations and normalized to 1 here is unique. There's only one such function. There's only one such geometrical sort of area. So as a result, this is the determinant of this matrix. Now let's go and look. You may have, let's see, look at the determinant of a general two-dimensional A, B, C, D. You may have, okay, well let's assume that all the row operations, that nothing's 0, so that we can always divide by these. So we can say this is equal to minus C over A, because we're going to cancel off A and cancel that times row 1 plus row 2. That should be the same as A, B, but then this is multiplying by minus C over A. Well, the A's cancel, minus C plus C is 0. And the one down here is going to be D minus B times C over A. Okay. Now, this is where it gets. Let's then multiply row 2, A times row 2. Okay. We have to do a little bit of special maneuvering because these are letters. Okay, well, that's going to equal, right? A times row 2. Well, that's going to equal, if I'm multiplying, it's like what I can do is, or better yet, what I can do is this. I can, since this is a 0 here, I can factor out this number. This is going to equal D minus B C over A times 0, 1, right? In other words, if this is true that our row operations work, then I can, whatever this number is, I can factor it out here, right? Then I can do minus B row 2 plus row 1, that will give me D minus B C over A times A 0, 0, 1, right? Now I can factor out the A here. This is going to give me, factoring out the, it will be A times D minus B C over A times 1, 0, 0, 1. Now, if I multiply the A in here, I have AD minus BC. Okay, times 1, 0, 0, 1, which equals AD minus BC. So if you look up here, we can say that the determinant of A, B, C, D equals AD minus BC. And I don't know if you remember this is a formula. But if you look up, this is the formula for a 2x2 determinant, right? Well, it turns out this formula is the area of the parallelogram defined by the AC and BD. It doesn't look like an area, but if I actually wrote out and tried to do the geometry, then it would work that way. We can go and do that with this. Let's see what happens here with 1, 2, 3, 4. And there is going to be something with this minus sign we have to worry about, but 1, 2, 3, 4. Let's look at 1, 2, 3, 4. Well, that should work with 1 times 4 minus 3 times 2 is 4 minus 6, which equals minus 2. Okay? So our previous calculation with Gauss's method it led to this formula, which is it's all consistent. It just agrees with what you think about what you may or may not know of determinants. Okay, so but the question is, let's look at this, see if we can look at this geometrically and verify that this one was 1, 3. So I go over 1 and up. Well, I might need more space. Okay. Here's some just coordinate axes. And then it is a 1, 3. Let's go over 1 here. Then 1, 2, 3. Okay, so I have this vector here is 1, 3. Then I have this one is 2, 4. 1, 2, and 3, 4. And I can see that that's going to be a terrible choice for trying to do the actual geometry of, right? Because it's like a little sliver. So let me choose. It's hard, so it's hard to see. Let's try to choose a geometric vectors that maybe make better sense, or they're easier to see what's going on. Okay. So I want something like, let's say, over 2. Yeah, I want, say, 2, 1, and say, you see, that's going to be 1, 2, and up 1. So that's a little bit better. And then let's say, how about 1, 2? It's going over 1, 1, 2 here, like this. So then, let me see, it goes over 1 and up 1, 2. So there's the parallelogram, right? So we really know what this area is, right? Well, and one of these points here. Well, this. Let's look at this length here, right? This is 2. But this is the other vector here. So this is 1, and this is 2 and 1. Okay, so this big rectangle here is 3 by 3 equals 9, right? So to get the area here, I need to subtract off there's a whole bunch of little spaces here I can subtract off. Like this is 1 by 1. This is this little rectangle. Let me see if I do. This is a 1 by 1 rectangle. This is a 1 by 1 rectangle. And you can see this triangle here is 1, this 1, 2. This is a 2 by 1, a 2 by 1, a 2 by 1, and a 2 by 1. So I have 4 times 1/2, 1 times 2, because that's the area of each of these rectangles. So what I'm going to have, the calculation is 9 minus 4 times 1/2, 1 times 2, minus 2 times 1. So this should be the area, right? So let's see what it is. It's 9 minus, well, this is the 1/2 times the 2, it's just going to be 4 minus 2 is 4 minus 2 is 6, 9 minus 6 is 3. Okay, then if I do the determinant according to the formula, which is just Gauss's method, it's going to be the determinant, if this matrix M, we'd say the determinant of M equals 2 times 2 minus 1 times 1, which equals 4 times 1, which equals 3. Okay, if you put in the general coordinates here, you could do the same calculation, but it would be a little bit unwieldy. for this. Okay, so the idea here is you can do the determinant here and then verify if it isn't too much of a slip. You could do this, but it'd be a little bit tedious because it's hard to draw a picture here. That the actual area you compute with Euclidean geometry, base times height of the formulas for triangles, rectangles to get this area of a parallelogram is going to be the same as the determinant of this matrix, this 2x2 matrix given by this formula. Okay, so now you could go through and begin to get formulas for for each one. But we have a method for finding, like let's say that we wanted to find a determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the determinant of this matrix? Right? Well, it turns out that if you look at all the different methods for calculating determinants, this is the volume of some parallelepiped. I've got three vectors in three-dimensional vector space, R's 3C, and they're gonna have some volume. If they're not linearly dependent, if one of them it'll be zero if that volume turns out to be not a full volume, right? The volume is zero. So let's see though, if just by using Gauss's method, right? So we're going to say equals, we can do -2 row 1 plus row 2 and -3 row 1 plus row 3. So that's equal to 1, 4, 7. So that's going to be a 0 here. And we're doing the same thing. We're aiming for echelon form. This is going to be -8 plus 3 is -3, right? -2 times 4 is -8. -8 plus 5 is -3. This is going to be -7, -14 plus 8 is -6, I think, right? -14. Okay, so -6. Then we do the same thing here. We're going to get a 0 there, right? We're doing -3 now. -3 times 4 is -12, right? -12 plus 6 is -6. And 3 sevens is 21. -21 plus 9 looks like it's going to be, let's see if it's -12. So it should be that -12 plus 21. Yeah, that looks right. Okay, so now what can we do now? Well, we can factor out, there's some common factors here. We can say this is equal to -3 times 1, 4. This will be under the row operation 3, row 2. It would actually be under the opposite, be -1/3 row 2 and -1/6 row 3 would be 3 times 0, 1, 2 and 0, 1. Let's see, is that, yeah, 2, right? And then this would equal -3 times 1. Or we can do
You have to multiply it by -6. Yeah.
Yeah, -6. Okay, times, yeah, let me -3 -6. And then what I'll do here is minus row 2 plus row 3, and this is going to be 18 there, times 1, 4, 7, 0, 1, 2, 0, 0, 0. Okay. Right, because I added -2 row 1 plus this. Now, this 0 row is interesting because what I can do is I can say, well, look, let's do this matrix here, 1, 4, 7, 0, 1, 2, 0, 0, 0. And what we do is we're going to look at that. We're going to factor out a 0 from this row, right? So this equals, right? Well, you don't have to, we can just do it this way. So I got the eraser right. One of the things I can do is I can factor out a 0 from this row. So this is going to be equal 18 times 0 times 1, 4, 7, 0, 1, 2, 0, 0, 0, which equals, this is some number, 0. You can see that any matrix that has a 0 row is going to have, because of this multiplication thing, has got to be 0. Okay? So the claim is that this matrix, this determinant here, 1, 2, 3, if I had made no errors, 5, 6, 7, 7, 8, 9 equals 0. Well, there's a formula for this, which if we went through and derived it, it's a little complicated, but we probably need to learn it just because it's a standard formula. Is what you do is you take, say we're going to expand on this is one particular. I'll show you the formula and show you that this will be the way to check that this result is correct. If I did this, make sure I did this correctly. That you can take a row and let's say play plus, minus, plus, and it's going to be, okay, let's say it's going to be 1 plus 1 times the 2 by 2 determinant of that one times the determinant of 5, 8, 6, 9. Then I don't need, it's going to be plus 1 times that minus 4 times the determinant of the 2 by 2 with the blue, which is a 2, 3, 8, 9, plus the 7 times the, let's see something colorful, plus the 7 times this form here, 2, 5, 3, 6. Okay, this is like some probably the Laplace explain. Anyway, so my point is there's various ways of getting this formula, but the point is that you can expand on any row or column and alternate signs, then take plus this, minus this, plus this, and then you can see if you take the leading number and remove that row and column, you're left with the determinant matrix here. So the 1 leaves this one. If I take out the 4, I have to take out the middle column and the top row, which leaves me with a 2, 3, 8, 9. If I take off the 7, that's the top row, the rightmost column, and left with the 2, 5, 3, 6. So it's harder to say than to sort of visually see the pattern. You have to sort of see the pattern and practice it. Okay, so let's say then this would be 5 times 9 minus 6 times 8 minus 4 times 2 times 9 minus 3 times 8 plus 7 times 2 times 6 minus 3 times 5, which is, so you can see that what's happening is, this is like a terrible expansion, although it's very common because you can see that you've had 3 terms with 4 by 4, and so you end up with all this arithmetic. It's going to be easy to make mistakes. Let's see, 5 9s is what, 45? 6 8s is 48. 2 9s is 18. 3 8s is 24. 2 sixes is 12, minus 3 fives is 15, right? So this should be minus 3 minus 4 times minus 6, right? This would be plus 7 times minus 3, right? And so then this is going to be minus 3 plus 24 minus 21, which equals 0, because 20 minus 21 minus 3 is minus 24. So this was a horrendous calculation that was gotten much more simply and easily with Gauss's method. Gauss's method is the most efficient way of calculating numerical determinants. So the formulas here, this one's useful to remember. A, B, there's also, you could write out this formula here for the 3x3 one. You know, you could write it out with A, B, C, D, E, F, H, I, J as A times E, J minus F, I, minus B times D, J minus H, F, plus C times D I minus HE. Okay, well, I should probably